Hello and welcome to the APL Quest. See APL Wiki for details. Today's quest is the second problem from the 2014 round of the APL Problem Solver competition. We're given a text and have to find the words in the text and remove any vowels from the words except if the vowel begins the word or the vowel ends the word. Let's get started with some test data. Okay. We can identify where we have spaces and non-spaces in our text. Then we can use this to partition the text, because partition will take elements, that is letters here, that correspond to runs of ones and group them together in a single element. Any letter or character that it corresponds to a zero will be discarded, and at this point we'll begin a new segment. So we partition using this mask. Now it's a question of processing each word separately. Because we need to be case insensitive, we have to handle all kinds of vowels, uppercase and lowercase. We can start by uppercasing our words. And we can then find out which letters are vowels. This gives us one mask per word. There's a problem, however. You can see that in the third word, the last letter is marked as a vowel, and we really don't want to consider the vowel that can be removed. Also, our masks are inverses of what we actually want. Since we're going to use compress to remove vowels, then we should have zeros for the characters we want to remove and one for those we want to keep. That part is super easy to fix. We just negate it. And then we need to take care of the issue of putting a 1 always at the front at the end. Well, that we can do. We can amend this vector with 1 at position 1 and also at the position of the length of the word. Now we're ready to do the compression. That looks good. We just need to join things together with spaces. Since we're already processing each word, we can just stick a space in front of each word, enlist the whole thing, and remove the leading space. This solution is nice in the sense that it expresses in APL very much how we think about the problem. Let's call it C for cut. There are other ways to address the problem, however, which avoids splitting up the text and processing in each word one at a time. Rather, the ideal when doing array-based programming is to process the entire array in one go. Let's see how we can do that. This time, we're going to start with uppercasing everything. And then we need to match up the previous letter and the next letter with the middle letter in order to identify whether or not we are at a word boundary. Of course, the first letter doesn't have a left neighbor, but we could possibly supply that. Now, in order to match up the left neighbor, the letter itself, and the right neighbor, we can drop. So here's the left neighbor. The left neighbor of the H in how is that space. If we drop 1, we get the H itself, and if we drop 2, then we get the neighbor on the right. We want to drop all 3 possibilities, 0, 1, and 2. And we want this dropping to be done on the entire vector. So we can say we want we want to drop using rank 0 every single number scalar from the left, and we want 1 because we want to treat the entire vector on the right. Now we can compare this whole matrix to spaces. For example, like this. We can put it inside the parentheses. And we know that a letter is internal if all these three, the left neighbor, this letter, and the next letter, or if the left character, the middle, the current character, and the right character, all are non-spaces. So we can combine this not equal with a vertical and reduction. The only problem we have now is that since we added a character, we have one character too many, and that we used this to push things to the right. And when we didn't drop enough, then one character from the end got pushed too far. We can see this above here. The last character we have is the U, and its left neighbor and its right neighbor. And here is another space that's been added, which we don't actually want. We can fix this, however, just by dropping the last element. Another way we could do it is by not adding the space on the left, because that will just give us all the information for all the characters except the first one. We know that the first character is not one that we should consider an interior character because it's right next to the beginning. So we can just add a 0 on the left, and that will give us the same result exactly. Now the only thing that remains is to check if the letters are also vowels. So we can do this by simply saying member of A-E-I-O-U, the vowels. That gives us this mask. And so these two masks are the ones we're going to combine. If a letter is both interior and it's a vowel, then that's a letter that we can remove. So let's combine the two parts. And this points out which letters we have to remove. But again, we want to use compress, so we want to mark instead the letters that we want to keep. We could negate it, but we can also just combine the negation with AND into NAND. Now we are ready to do the compression. That works very nicely. Let's call this one drop, D for drop, because we're using drop in various places. We talk about these neighbors, and we look at these triplets. Another way to do this is by using n-wise reduce. So let's start over with our text and uppercasing it. We can look at triplets. Initially, we can try just concatenating them together. So these are the triplets. But instead of applying this n-wise reduce on the letters themselves, let's do it on the Boolean mask of whether there are non-spaces. And now we just need to reduce each one of these with an AND reduction, just like we did before. We don't need to do this outside of the n-wise reduction, because n-wise reduction is indeed a reduction on each sliding window of this size, 3 in our case. And that gives us the mask for which letters are interior letters, which means we can just combine all of this with our way of finding the vowels in exactly the same way. Oops. Oh yeah, of course. Since we have sliding windows that don't that begin at the very left edge, and we have sliding window size 3, that means that we don't have a corresponding element for the very leftmost and very rightmost letters. But we know that those are boundary letters, and so we can just supply those. That gives us our mask, and we're ready to do the compression just like we did before. Let's call this one R for reduction, NY's reduction. Another way to look at neighborhoods is using stencil. So let's try this again, uppercasing that. And this time we're going to use stencil. And stencil with a window size of 3 and applies its operand on each sliding window. At the edges, if necessary, it pads. And it is necessary in our case. We want window sizes of 3, and every element gets a chance to be the center of a neighborhood of size 3. Stencil will pad with an appropriate padding, which for text is spaces. And that's great. That's exactly what we want. What operand are we going to give to stencil? We're not interested in the left argument to the operand, which is the padding information. We just want the right argument. And we want to know where it is all true that the letters are different from space. That gives us our mask, including the zeros. So this is exactly what we had before with the endwise reduction, and we can just copy the rest of our code in. This is our stencil S function. Now it would be interesting to compare the performance of these, wouldn't it? Let's do that. For our test case is tiny. We also need to generate some larger test data. So now I'm going to copy in the CMPX utility which measures performance, and also for convenience I'll have the delete extraneous blanks in order to generate our test data. Copy those from the defense workspace. Okay, for our test data, let's have some uppercase characters and some lowercase characters. And then we need to have some spaces as well, in a nice proportion. I'd say if we take about 60 and overtake, then we get a bunch of spaces at the end. Then let's choose some random ones from this. So random, we'll take 1,000 of those from all of them, the length of that. So this gives us a bunch of letters. If we just take the first 100 of those to have a look at what they could look like, we can see here at the end we have some double spaces. So that's why we need to apply delete extraneous blanks, and then that won't happen. No more double blanks. Okay, then we're ready to assign this. It's not, even though I asked for 1,000, it's of course not exactly going to be 1,000 because we are deleting some spaces here and there, but it's close enough for our purposes. Let's generate some APL expressions that we're going to compare the performance of. We had C for the cut method and D for the drop. We had R for reduce and S for stencil. Each one of those is going to be called on the entirety of this test data here. So these are our 3 APL expressions, and now we're running the timings on those. See what that looks like. All right. Well, that's pretty significant differences we've got there. The cut method, which was our baseline, is not very good compared to using drop and reduce. That's because drop and reduce are entirely flat solutions, whereas when we cut into individual words, then we get a pointer array, one pointer per word, and that's going to be very expensive to traverse. So that one's basically out. There's nothing we can do to fix that. Stencil, that doesn't look good at all. And the reason is that we gave a rather complex operand to stencil. And there are just a few common patterns that, when expressed as defense, have been optimized very heavily, and they'll give us way better performance. So let's see if we can use one of those instead. So I know that one thing we can do with stencil that's super fast is just getting the right argument. Now, since we have neighborhoods of 3 from a vector, that means every such neighborhood is a vector in itself, and stencil will collect them into an array where the major cells are these vectors. So an array that consists of vectors is a matrix. We'll get one neighborhood per row. And all we need to do now is the exact same thing here. We're just comparing to spaces, and then we are reducing across the rows. So all this should just work in exactly the same way. And let's try it on our small test case. Oops. Yeah, I made a mistake here. I am missing a space. No, not missing a space. I have a parenthesis that could be missing, or we can just remove this parenthesis over here. That's why it was red before. Okay, let's try it again. There we go. Now it works. Right. So, let's do this comparison again with the new updated stencil version. But this time we're going to skip the one that cuts using partition, because that's hopeless. Stencil is still the slowest of the 3, but it's not bad. Right? They're all very similar to each other. And if something is convenient to express using stencil, then by all means, it can work very nicely. And then you don't have to worry about how much padding you need for various sizes, which you didn't need to worry about for the NYS reduce. But there's another problem, and that is, let's update our small test case with some punctuation. The problem here is with the final letter. Since we are detecting where there are the characters that are non-spaces, then question mark is a non-space, and U will be considered an internal letter. So, for example, using this S, we can see that O and U get removed, which is of course wrong. So, how can we fix this? Well, here are our definitions. The problem is that we are using the property of being a non-space to identify which characters are eligible to be removed and which ones have non-space neighbors. And we really want to turn it upside down. We want, in order for a character to be considered an interior letter, it's the determining factor there is that its neighbors are also letters, not just non-space characters, but letters. So we just need to turn things around a little bit. For the dropping method, the only thing that we need to do is to check if characters are in the set of uppercase letters, and membership goes the other way around, so we can swap that. And if they are letters, all of them, then we have an interior letter. And actually, the exact same thing applies to all of these solutions. So here, with n-wise reduce, instead of checking whether we have non-letters, we just look whether or not they are members in the uppercase alphabet. And so too, with stencil, instead of checking whether or not we have non-letters, we just check whether or not they are members of the uppercase alphabet. And now we can generate new test data. So this time we're going to have uppercase letters and lowercase letters, and also some punctuation. Let's say 65, or we're taking that to get some spaces there, and then we just use the same formula as before. We want random about 1,000 of the length of the argument. And this time we don't need to remove extra blanks. Right? The comparison we're going to do is exactly the same as before. And the performance is very similar to what we had before. But this time we are correctly handling all of these. So we can see it, for example, with the dropping on T, and reduce on T, and stencil on T. We can see that the U remains right there. So these are some good solutions, APL solutions. There's another approach though, and sometimes it's more convenient, and that is to use regular expressions. And we found two interesting ways of doing this using regular expressions. What we can do is we want to look for some characters, and then we want to remove them, and we want to do so case insensitively. The letters that we want to remove are the vowels, but we don't want to remove all the vowels. We want to make some assertions about these vowels. What we want to assert is that this question, whether on the left we have a word character. If there's not a word character on the left, then we're not interested in this vowel. That also means is the first character in the input, then we're not interested in it. We also want to make sure that on the right we have a word character. If it's the last character in the whole input, then there are no characters to the right, and we're also not interested. It's important to note that these look-arounds, or look-behinds, look-aheads, are not part of what's being matched. They're just something that's being checked when we try to match them. So that works as intended. It can be hard to think about these assertions. I personally find it easier to think about things in a different way, and that's with what you could call exception patterns to detect things and let them go through. So again, we do want all the vowels, and we want them removed, but we want to preserve some. Which ones are that we want to preserve? We want to preserve any letter that is preceded by a word boundary. So that means it's on the left edge of a word, or at the right edge of a word. So those will replace with themselves. And any vowel that remains after that hasn't been consumed by the first pattern, we're going to replace with nothing. So let's call this one B for word boundaries, and the one we had before, we'll call it A for look arounds. And then we can compare the performance of these. So now we have drop, we have reduce, we have stencil, and then we have look arounds and word boundaries. Each one we're going to run on the entire expression of on the entire argument of T3. And we can, oh, we even didn't get the exact same result. Why is that? This is look ahead. Oh well, that's interesting. This works. Well, let's do some debugging and see what's happening here. We can start with some of our string. So if you take 100 from T3, and then we can, oh, so we can even do it like this. We can say, is D matching A for 100 of T3? No. Is it so for 50 of T3? How about for 20? Yes. 25? No. Okay, so now we can look at 25 take T3 and see what is it that's oh, this is at the very first space. At the very first space. So D removes the internal vowels, like this O, for example. And A. We removed one more thing than D. Where are they different? Oh, did I simply forget an I? Oh, D didn't remove the I. That's interesting. This I doesn't get removed. But we clearly have an I here. It removes it. Uppercase I gets removed. So what's going on here? Why is D not removing this? Oh, I see. It's because did I put in digits by mistake in our test data? That's what it is. So, oh yes, I put in a 1 over here. That should have been an exclamation point. So much for that. That was some troubleshooting right there. Let's try the performance again. But of course, it shouldn't really make a big difference in the results that we get. There we go. Now we can see it, finally. The performance using regular expressions is not good compared to the APL solutions. And with multiple patterns, it's even worse than with a single pattern with lookarounds. But hey, sometimes Regex is the way to go, especially if it's a smaller amount of data, or it's something that's very complex to express, or it's something you just need a one-off and not running a lot of times, then it could be quite fine. But we should definitely prefer an array-oriented solution if at all possible. Thank you so much for watching.